Limits are a tool that help us to describe the behavior of a function as our x values approach a particular number. So remember, if you're looking at a graph, if you see an open circle, it means that that point is not included on your graph. But a closed circle means that that point is included on your graph. And so here we have the graph of a function f of x, and notice that there is an open circle at 0. So this function is undefined at 0. So f of 0 doesn't exist. But even though f of 0 doesn't exist, we can talk about what's happening to our function as x gets really close to 0 from either side. And so as you follow this graph, notice that as x gets really close to 0, your y values are also getting really close to 0. So we would say that the limit as x approaches 0 of this function is also equal to 0. So the notation we would use, we would write LIM for limit. We would say the limit as x approaches 0 of f of x is equal to 0. And this just means as x gets really close to 0, the function gets really close to 0. So it gives us a way to talk about the behavior of our function near 0, even though we can't talk about f of 0 for this particular example. So again, if I'm looking at the graph of a function, and maybe it looks something like this. And I want to look at what happens as x approaches a. Well, if we say the limit as x approaches a of f of x equals L, that means as x gets really close to a from either side, my function value is going to get really, really close to L. And so I can get as close to L as I want to by choosing values of x that get closer and closer to a from either side. So when we were looking at this graph earlier, we determined that as x gets really close to 0 from either side, our function value also approaches 0. So the limit as x approaches 0 of f of x is equal to 0. Now, if you look here when x is 4, you see that the function is defined at 4, so f of 4 exists, but there is a jump in our graph at that point. And if you look at what happens as x gets close to 4 from either side, our function is actually approaching 1, it looks like. So we would say the limit as x approaches 4 of f of x is equal to 1, even though f of 4 is actually equal to 3. So remember, the limit as x approaches a value does not necessarily have to equal the function value at that point. We can also talk about one-sided limits, where we're approaching an x value from only one side. So the notation we use looks like this. When you see this little minus sign, this little superscript, it indicates that we're approaching this x value from the left, or from the negative side of the x-axis. And when you see this plus sign, it means that we're approaching that x value from the right, or from the positive side of the x-axis. Again, we're using our example at 0. As x approaches 0 from the left, the function also approaches 0. So we would say that this one-sided limit, the limit as x approaches 0 from the left of f of x, is equal to 0. And as x approaches 0 from the right, the function also approaches 0. So the limit as x approaches 0 from the right of f of x is also equal to 0. And remember, we've already determined that this two-sided limit as x approaches 0 of f of x is equal to 0. And so if we look at what's going on when x is 1, you can see that as you get close to 1 from the left or from the negative direction, your function value gets really, really close to 1 as well. So we have the limit as x approaches 1 from the left of f of x is equal to 1. And then if you look at what happens as x approaches 1 from the right, well, now our function is way up here. And so as x gets really, really close to 1 from this positive direction, the function is actually getting really, really close to 3. So the limit as x approaches 1 from the right of f of x is equal to 3. But now, remember that if I write something like the limit as x approaches 1 of f of x, that's a two-sided limit. So I'm talking about what happens as x approaches 1 from either side. And you can see here that we're not approaching the same value as x approaches 1 from the left and the right. So that means that this limit does not exist. So remember, the two-sided limit can only exist if both of the one-sided limits exist and they're equal to one another. So your function has to be approaching the same value from the left and the right in order for the two-sided limit to exist. So here's another example. We're given the graph of some function f of x, and we're asked to evaluate each of the following limits. So first we want the limit as x approaches -1 from the left of f of x. So if you look at the graph, when x is getting really close to -1 from the left, your function is also getting very close to -1. So we would say the limit as x approaches -1 from the left is -1. And as x approaches -1 from the right, you can see that your function is also approaching -1. So we can say the limit as x approaches -1 from the right of f of x is -1. Now, since both one-sided limits exist and they agree with each other, then that two-sided limit as x approaches -1 of f of x is also going to equal -1. Now, if we take a look at the limit as x approaches 1 from the left, well, you can see that as x gets really, really close to 1 from the left, your y values are getting really, really close to +1 as well. So the limit as x approaches 1 from the left of f of x is equal to 1. Now, as x approaches 1 from the right, it looks like your function is way up here. So as x approaches 1 from the right, your function values are actually approaching 3. So the limit as x approaches 1 from the right of f of x will equal 3. Now in this case, the one-sided limits do exist, but they don't agree with each other, which means the two-sided limit, this limit as x approaches 1 of f of x, does not exist. So I'm going to write DNE for does not exist. So then if you look at the limit as x approaches 4 from the left, we're way up here. So as x gets closer and closer to 4, your function values also get closer and closer to 4. And as x approaches 4 from the right, your function values again are approaching 4. So the limit as x approaches 4 from the right of f of x is also equal to 4. And since both one-sided limits exist and agree with each other, then that two-sided limit will also equal 4. And so one thing I want to point out, if you look at this first set that we looked at the limit as x approached -1 from the left and the right, you notice that the function is not defined at -1. The function wasn't defined, but the limit did still exist. So remember, it is possible for the limit to exist even if the function is undefined. Now at 1, the function was defined, right? But there's a jump in the graph, right? So the limit didn't exist. The limit didn't exist because the function was approaching different values from either side. And here we have another example. We have a graph of a function f of x, and we're first asked to evaluate the limit as x approaches 10 from the left of f of x. And so here it looks like each tick mark on the graph is worth 5 units. So 10 would be here on the graph. So if we look at what happens as x approaches 10 from the left, you see that your graph is growing without bound. So as x approaches 10 from the left, your function values are continually getting larger and larger, so they're actually going to be going towards infinity. And the same thing happens as x approaches 10 from the right. As x gets closer and closer to 10 from that positive direction, your function values are growing without bound. So we're going to say the limit as x approaches 10 from the right of f of x is also equal to infinity. Now here, since the one-sided limits exist and agree with each other, that two-sided limit will also exist. And so the limit as x approaches 10 of f of x will also equal infinity. Now note, technically infinity doesn't exist, right? Infinity is not a number, but it gives us more information about the problem. So when you're evaluating limits, if you can possibly give positive or negative infinity as your answer, that's what you want to do. You want to save that DNE, or that does not exist answer, for when the limit truly doesn't exist and you can't give any more information. So if we take a look at another example, here we have the graph of the function f of x equals x minus 3 over x minus 2. And we want to look at the limit as x approaches 2 from the left of this function. And so if you look at what happens as x gets really close to 2 from that negative direction, it looks like your function is going to grow without bound. So we would say that the limit as x approaches 2 from the left of this function is infinity. And if you look at what happens as x approaches 2 from the right, so now you're coming from this positive direction, it looks like your graph is going to grow in magnitude, but it's negative. So we would say the limit as x approaches 2 from the right of this function is negative infinity. And so you notice that the one-sided limits don't agree with one another. So that means the limit as x approaches 2 of this function does not exist. And if we look at another example of evaluating limits using a graph, here we're given the graph of a function y equals h of x. And then first we're asked to find h of 4. Well, remember, h of 4 is the function evaluated at 4. And so on the graph, if you look, you see when x is equal to 4, the function is actually defined to be 8 because we have this closed circle here. So h of 4 is equal to 8. And then in part B, we're asked to find the limit as x approaches 4 of h of x. So we want to look at what happens as x approaches 4 from both the left and the right. And you can see as x is getting close to 4 from the left, your function values are actually getting close to 6. And as x approaches 4 from the right, there again, your function values are getting close to 6. So the limit as x approaches 4 of h of x is actually equal to 6. So here's another example of a case where the limit exists, but it doesn't equal the function value at that point. Now, h of 7, well, you see it when x is 7, we have this open circle. There's no other closed circle when x is 7. So our function is not defined at 7. So h of 7 does not exist, or it's undefined. But the limit as x approaches 7, if you look as x approaches 7 from the left, your function values are getting close to 3. And as x approaches 7 from the right, your function values are also approaching 3. So the limit as x approaches 7 of h of x would be equal to 3. So here we see an example of a point where the limit exists, but the function is undefined. And then we're asked to find the limit as x approaches 8 of h of x. And so as x gets really close to 8 from the left, the function is getting really close to 4. And as x approaches 8 from the right, your function values are getting really close to 4. So the limit as x approaches 8 of h of x is equal to 4. And you'll notice from this graph that h of 8 is actually equal to 4. So in this case, the limit as x approaches 8 of h of x is actually equal to the function value at that point. Oh, true or false? So when the limit as x approaches a of f of x exists, it is always equal to f of a. So this question is asking us, when the limit as x approaches a of f of x exists, does it always equal the function evaluated at a? And of course, the answer to this question is false. You've already seen a couple of examples. Notice here in this graph, if we look at what happens when x approaches 4, we know that the limit as x approaches 4 of this function, call it f of x, is equal to 1, right? But you can also see that f of 4 is equal to 3. So this is an example of a point on a function where the limit does exist, but it does not equal the function value. So here we're given a piecewise function, g of x equals x squared when x is less than or equal to 1, and x plus 2 when x is greater than 1. And we're asked to evaluate the limit as x approaches 1 from the left of g of x, and the limit as x approaches 1 from the right of g of x. So remember, a piecewise function is just a function that's defined differently for different pieces of the domain of your function. And so our g of x, it's defined to be x squared when x is less than or equal to 1. So on our graph, for all values of x that are less than or equal to 1, the graph looks like the graph of f of x. Now, since g of x is defined to be x squared when x is less than or equal to 1, that means I'm going to put a closed circle here, because when x is equal to 1, the graph is defined to be x squared. Now the function is defined to be x plus 2 when x is greater than 1, strictly greater. So I'm going to put an open circle here at 1. Then for all values greater than 1, the graph looks like the graph of x plus 2. So when we want to find the limit as x approaches 1 from the left of g of x, using our graph, you can see that as x approaches 1 from the left, the function approaches 1 as well. So that limit as x approaches 1 from the left of g of x is equal to 1. And the limit as x approaches 1 from the right of g of x, you can see as x gets close to 1 from the right, your function values are getting close to 3. So the limit as x approaches 1 from the right of g of x would equal 3. Now, another method for evaluating limits is by using a table. So in this example, we're asked to find the limit as x approaches 2 of f of x, where f of x is equal to x cubed minus 2x squared over x minus 2. So on the table, we have x values, and then we have the corresponding function values. Now notice it's blank at 2 because this function is actually undefined at 2. If we plug in 2, we would be dividing by 0. So we have x values that are getting close to 2 from the left, and we have x values that are getting close to 2 from the right. And so as x gets really, really close to 2 from the left, does it appear that your function values are approaching a particular number? Well, in this case, it looks like our function values are getting closer and closer to 4. So we could say that the limit as x approaches 2 from the left of f of x is equal to 4. And as you approach 2 from the right, it again looks like your function values are getting closer and closer to 4. So we can say the limit as x approaches 2 from the right of f of x is equal to 4. And since both of the one-sided limits exist and they agree with each other, that means that this two-sided limit, or the limit as x approaches 2 of our function, will also equal 4. Now in the previous example, we were given a completed table. In this example, we have x values and we need to fill in the corresponding function values so that we can determine if our function appears to be approaching a specific value as x approaches -3. So we have the function f of x equals x cubed plus 27 over x plus 3, and we want to evaluate the limit as x approaches -3 of f of x. So we can use our calculator to evaluate our function at each one of these values. So in our graphing calculator, we are going to graph our function. So I'm going to hit y equals, and I'm going to put the numerator in parentheses, so that was x cubed plus 27 divided by x plus 3. So I've got my function typed in. Now in blue it says table set, so I'm going to choose second table set. Now notice it's asking me if the independent variable should be set to auto or ask. So I'm going to choose ask because I want it to ask me what values to use for the x variable. Then I'm going to hit second table. And so it's giving me an x column and a y column. So now I can type in the x value that I want, and the first value on our table was -3.1, and hit enter. And it's telling me the y value is 27.91. Now if I type in -3.01 for x and hit enter, it's telling me that my y value is 27.09. So we can continue completing our table using the graphing calculator. So we can fill in the values that we just calculated. When x was -3.1, our function value was 27.91. When x was -3.01, we got 27.09. If I type in -3.001, I get 27.009. So as we get closer and closer to -3 from the negative direction, it looks like our function values are getting closer and closer to 27. So we could say the limit as x approaches -3 from the left of our function f of x is equal to 27. And then coming from the other direction, if we look at -2.9, it looks like the function is going to be 26.11. And if we plug in -2.99, the function value, it looks like 26.91. And if we do -2.999, we get 26.991. So as we get closer and closer to -3, coming from the right, it again looks like our limit is going to be 27. So we have the limit as x approaches -3 from the right of f of x equals 27. So we can say the limit as x approaches 3 of our function f of x is 27. Now, there are some rules for limits or properties of limits that you're going to want to be familiar with, because these are going to help you to evaluate limits in this unit. So if we let f of x and g of x be two functions, and we're going to let a be a real number such that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. So the first property says that for any constant k, the limit as x approaches a of k is k. Meaning if you have a constant function, no matter what x approaches, your function is approaching that constant. It also turns out that if you take the limit as x approaches a of a constant times a function, you can sort of pull that constant out front. You get the constant times the limit as x approaches a of that function. The second property says if I want the limit as x approaches a of two functions that are being added or subtracted, that's really the same thing as taking the limit as x approaches a of f of x and then adding or subtracting the limit as x approaches a of g of x. The same kind of thing works with multiplication. The limit as x approaches a of these two functions being multiplied together is the same thing as taking the limits separately and then multiplying. And if we want the limit as x approaches a of two functions being divided, it's the same as taking the limit as x approaches a of the numerator and the limit as x approaches a of the denominator and dividing those things, provided, of course, that we are not dividing by 0. The fifth property on our list says that if we have a polynomial function p of x, then the limit as x approaches a of p of x will just equal p of a. So we can evaluate the limits of polynomial functions by direct substitution. And if you think about it, polynomials are nice and smooth and continuous. They don't have any holes or breaks or jumps or anything weird going on. Then number 6 says if we have any real number k, then the limit as x approaches a of a function being raised to a power is the same thing as taking the limit as x approaches a of that function and then raising that to the power. And property number 7 says if f of x equals g of x for all x not equal to a. That just means that these two functions are equal everywhere except at a. Then the limit as x approaches a of f of x and the limit as x approaches a of g of x will be equal. So here they're telling us that the limit as x approaches 4 of f of x is equal to 9, and the limit as x approaches 4 of g of x is equal to 27. So if we want the limit as x approaches 4 of f of x minus g of x, remember that's the same thing as the limit as x approaches 4 of f of x minus the limit as x approaches 4 of g of x. And we know the limit as x approaches 4 if f of x is equal to 9. And we know that the limit as x approaches 4 if g of x is equal to 27. So we have 9 minus 27, which is equal to 18. For another example, if we want the limit as x approaches 4 of 5 times g of x plus 2, well, we know that this is the limit as x approaches 4 of 5 times g of x plus the limit as x approaches 4 of 2, which is the same thing as 5 times the limit as x approaches 4 of g of x plus that limit as x approaches 4 of 2. And we're given in the problem that the limit as x approaches 4 of g of x is 27. So this is 5 times 27 plus, and 2 is a constant, so the limit as x approaches 4 of 2 is just 2. So we have 5 times 27 plus 2, which is 137. So in this example, we want the limit as x approaches 0 of x to the 4th plus 3x plus 1. So x to the 4th plus 3x plus 1 is a polynomial function, and so that means we can evaluate this limit by direct substitution. So this would just be 0 to the 4th plus 3 times 0 plus 1, which is just 1. So here we are given the piecewise function g of x equals x squared when x is less than or equal to 1, and x plus 2 when x is greater than 1. And we're asked to find the limit as x approaches 1 of g of x. So notice this function is defined differently on either side of 1. So to evaluate this limit, I am going to start by first finding the limit as x approaches 1 from the left of g of x, and then the limit as x approaches 1 from the right of g of x. Now, if we're approaching g of x from the left, we would be coming from that negative direction, and so the values of x would be less than or equal to 1. So to evaluate the limit as x approaches 1 from the left of g of x, we'll be using this top piece of our function, this x squared. So we really want the limit as x approaches 1 from the left of x squared. And since x squared is a polynomial function, we know that we can evaluate this by direct substitution to just get 1. And when we want to find the limit as x approaches 1 from the right of g of x, well, now our x values will be greater than 1, so we're going to be using this second piece of our function. We'd have the limit as x approaches 1 from the right of x plus 2, which again, x plus 2 is a polynomial, so we can evaluate this by direct substitution to get 3. Now, since the one-sided limits don't agree with each other, we have the limit as x approaches 1 of g of x does not exist. So here we are given a piecewise function g of x, and we've been asked to determine a value of the constant a for which the limit as x approaches -1 of g of x exists, and we're asked to state the value of the limit if possible. So g of x is defined to be x squared minus 8x when x is less than or equal to -1, but it's defined to be ax cubed minus 9 when x is greater than -1. So we're asked to find a value for this constant a that forces the limit as x approaches -1 of g of x to exist. So remember, in order for this limit to exist, we need the one-sided limits to exist and to agree with one another. So we can start by finding the limit as x approaches -1 of g of x from the left. And if we're approaching from the left, we're coming from values that are less than or equal to -1. So we want the limit as x approaches -1 from the left of x squared minus 8x, which we can evaluate by direct substitution because x squared minus 8x is a polynomial. So we would get -1 squared minus 8 times -1, which would be 1 plus 8, so 9. Now, in order for this limit to exist, we would also need the limit as x approaches -1 from the right of g of x to equal 9. So that means we would need the limit as x approaches -1 from the right of ax cubed minus 9 to equal 9. Because if we're approaching from the right, the x values will be greater than -1. And so if we look at the limit as x approaches -1 from the right of ax cubed minus 9, we can evaluate this by direct substitution because it's a polynomial. So if we plug -1 in for x, we would have a times -1 cubed minus 9. And we want this to equal 9. So we would get negative a equals 18, which would mean that a equals -18. And so if a is equal to -18, then we would have the limit as x approaches -1 from the right of -18 x cubed minus 9. And this would be -18 times -1 cubed minus 9, which would equal 9. So the value of a that forces continuity for this function at -1 would be 18. And the value of the limit would, of course, be 9.